So this is part 2 of my series on writing and loading eBPF bytecode. We'll backtrack a little bit from the end of the last one. So the bytecode at the top here, basically all of this to here is just setting up a function call. So first of all, we put the file descriptor into the register number 1, and next we want to put a value on the stack, and we take a pointer to that value on the stack and pass that to the function. This function, BPF map lookup, the first argument is the file descriptor, which is just an integer, and the second argument is actually a pointer to some memory where the map index or the map key should be located. So here we actually, first of all, we put the frame pointer into register 2, so we can operate on it, and then we subtract 8 from the frame pointer, which gives us an address that's 8 places removed from the top of the stack. And then we load onto the stack the value 0. BPF forces us to do this. The stack is not zeroed, or rather the verifier won't allow us to make accesses to the stack which haven't been set yet. So you can't read from the stack until you've set some memory there, which is a basic safety precaution. So yes, then map lookup element will look up this pointer value, and the return value from map lookup element will contain another pointer or 0. If it's 0, that means it failed for some reason, and this next instruction tests if register 0 is equal to 0, and if it is, then it jumps, and it jumps 3 instructions from the current program counter value to the end. So it jumps from this place to the exit instruction. But assuming it's successful, we then want to set map values 0 to 1, which is part of the test. After this program has been run, we check whether this map value's been set. So the pointer value which is returned, we can actually write to this, and this will write to the underlying map. So in the first case here, we move the pointer value from R0 to R1, so as not to interfere with R0. And then we store 1 to that memory location. And then we move 0, or rather we set R0 to 0 because it's the return value for our program overall, and we set it to 0 to indicate success. And yes, we then return. This instruction just indicates to the verifier that this is the intended end of the program. Okay. So if we look down here at where we load this program, we have a global variable here, which is where we store the the program. This is different from this static variable here where I've written the bytecode. As I mentioned before in part 1, this test uses the guarded buffers API, which creates a buffer object which contains a canary zone at the beginning of the buffer and a page at the end of the buffer, which is supposed to catch accesses by the kernel that are either before or after the area which the user has designated as a buffer object and passed to the kernel, and accesses by the C library. So it just helps with debugging the kernel and C library, and also it will catch any errors in our program as well. So we copy the prog static variable to the prog buffer, which the LTP library allocates for us, and up here you can see in the setup function where we actually copy the memory, which means when we get to this point, when this function is called, we know what the file descriptor will be for our map, and we overwrite the first instruction with a new instruction with the correct file descriptor. And then we put this into an attribute, a BPF attribute structure, which is passed to the BPF system call, or it's a union of different possible attributes for different BPF commands. We also pass some other stuff like we set up a log buffer so that if the BPF verifier finds some problem with our program, it can write out to this buffer we've allocated some information about what it found wrong. And actually, if there's one good reason why you should learn how BPF bytecode itself functions, it's so that you can understand these log messages. Because the verifier itself will just point to problems in the bytecode. It won't tell you if you're writing your BPF programs in C or some other language, then the kernel itself doesn't understand these languages, as far as I know anyway. There is in fact a BTF annotation, so you can maybe match the bytecode to the original lines of source code in the C program, but it still helps to understand what the bytecode is doing. Okay, so we load that maybe, and then once that has been loaded, we attach this program to a socket, and we send a packet on this socket which should activate the program, and then we check to see whether the map element has been accessed, whether the map element has been set to 1. If the program wasn't run or the program failed for some reason, then obviously the map element will just be 0. Well, it's actually an array, and BPF array maps are zeroed by default, so all the values in there will be 0 to begin with. Okay, so now that we've covered the most basic program you can really create, this BPF prog2 is another test which looks at a known BPF problem, a known bug. I'm not sure it's a bug that is very likely to occur in the wild, but it just happens to be one that we found, and it's quite easy to create a test for this. So someone at Cloudflare managed to find that BPF couldn't perform basic arithmetic when a BPF program is loaded as a non-root user. And you can look at this blog article if you want to see exactly what's going on there. I won't fully attempt to explain why this happens. But basically, the verifier rewrites your bytecode to avoid some kind of attack with Spectre and speculation when you're doing pointer arithmetic. And even if you're not doing pointer arithmetic, the bug causes your bytecode to be rewritten, which causes large 64-bit ints to be added or subtracted incorrectly. So what this test does is we take a large 64-bit integer and we add and subtract it inside BPF, and we write the result of adding and subtracting that value to two entries in a map, and then we check that those values are correct. And you can see here that the bytecode for this is a bit more complex. We still have the same code here, which loads the pointer to our map, and then after this we have some code which simply just performs a 64-bit addition. So we load in our 64-bit value using a special instruction which allows us to load a 64-bit immediate. If we look down, this is defined here. So again, we have this, we actually see this as two instructions. We have the first instruction which specifies what kind of instruction it is. And then we have a second instruction with just a 0 code which contains the higher bits. And we then have an instruction which specifies that we want to perform an add operation from between registers 4 and 6, with the result being stored in register 4, and we then save this value to register 3, where, or rather we don't save it to register 3, we save it to the memory location where register 3 points, which is inside our array map. And then the second half of this bytecode simply does the same again, but for subtraction rather than addition. So I've just copied and pasted these two sections. So this bytecode could be quite a bit shorter, but sometimes copy and paste is the easiest way and most robust. And then again, we just have setting 0 and returning. One thing that can catch you out with these types of programs where you have immediates where you're loading a 64-bit value is that because this immediate and I think not that one. Okay. Okay, this immediate just here, because these are actually two instructions, when you're specifying your jump value here, which is 17, you have to bear in mind that you can't just count these lines, as these are just macros. You have to add an extra instruction for each of these 64-bit immediates. So if you actually count these lines, it won't be 17 until the end, it will be 2 or 3 less than that. Okay. Okay, you can see the code here is slightly different for this program, but otherwise it's fairly similar. And that is the end. As I mentioned in the first one, or as I mentioned in the comment on YouTube, although I'm using the LTP library, you can of course write a C program without any of the LTP library and just use the C standard library. And if we look at, so if we look at this BPF function here, we can see that this is a very simple function which just makes a call to test system call. If we look at this function, this is basically just making a call to the general system call function with the system call number, and you can easily copy and paste this into a new project, or you can just define BPF as syscall and then write in the syscall number. So you can recreate this program without the LTP library and just copy and paste in the headers that you need. So you can create a program that loads and uses BPF bytecode with almost no dependencies apart from the C standard library. Okay, I think that's it. I haven't these tests haven't been included in the LTP at the time of writing, but they will be soon. Thank you for watching until the end.